Picture this. It's 1965, and you're standing at the starting line of a drag strip. The car next to you doesn't sound like a car. It sounds like mechanized death. The ground is literally shaking. The driver gives it a blip of throttle, and the concussion hits you in the chest like a physical force. That's because this isn't a car engine. It's 1,190 cubic inches of air-cooled fury ripped straight from the guts of an M47 Patton tank, and some absolute madman just strapped it to four wheels and pointed it down a quarter-mile strip. Welcome to one of the most insane chapters in drag racing history, when racers decided that conventional engines weren't enough. They wanted more. They wanted tank engines. The Continental AV-1790 wasn't just big, it was a monument to excess. We're talking about a V12 air-cooled monster that displaced 29.3 liters. That's nearly 8 times the size of a modern Corvette engine. This wasn't an engine designed for acceleration or speed. It was designed to haul 46 tons of armor across battlefields while being shot at. It produced 810 horsepower at just 2,800 RPM, with torque numbers that could twist a normal chassis into a pretzel. But here's where it gets interesting. In the mid-1960s, the U.S. military was phasing out its M47 Patton tanks, replacing them with the newer M60s. Suddenly, surplus depots were flooded with these Continental power plants. You could pick up an engine that cost the government $30,000 to build for about $500. That's $4,600 in today's money for 810 horsepower. The drag racing community took notice. To understand why anyone would think this was a good idea, we need to travel back to the Wild West days of drag racing. This was before NHRA had comprehensive safety rules, before funny cars, before Don Garlits lost half his foot and revolutionized dragster design. This was the era when innovation meant survival, and the only rule was to go fast or go home. The dominant engines of the day were heavily modified Chrysler Hemis, blown Ford flatheads, and the occasional Cadillac or Oldsmobile V8. A top-fuel dragster in 1965 might make 1,500 horsepower if everything was perfect, but that required exotic fuel, massive superchargers, and constant rebuilds. These engines would grenade themselves regularly. Pistons would become projectiles. Connecting rods would exit through the oil pan. You'd rebuild between every run if you were lucky, between every half run if you weren't. The Continental AV-1790 offered something different. Sure, it only made 810 horsepower, but it made it reliably. This engine was designed to run for 500 hours between overhauls in combat conditions, in the desert, while being shot at. With minimal maintenance, it could run at full throttle indefinitely without breaking a sweat. For drag racers used to engines that lasted seconds, this was revolutionary. But the engineering challenges were staggering. First, the weight. The AV-1790 tipped the scales at 2,950 pounds dry. Add fluids, and you're looking at 3,100 pounds. A complete top-fuel Hemi of the era weighed maybe 600 pounds. The tank engine was heavier than most complete drag cars. Then there was the size. The engine measured 67 inches long, 39 inches wide, and 36 inches tall. It was designed to sit in the hull of a tank, not the chassis of a dragster. The cooling system alone was a nightmare. This was an air-cooled engine that relied on massive fans and carefully ducted airflow in the tank. In a dragster, you had to figure that out yourself. The power delivery was completely wrong for drag racing. Tank engines are designed for constant speed and massive torque at low RPM. The AV-1790 produced peak horsepower at just 2,800 RPM and would mechanically explode if you spun it past 3,200. Your average small block Chevy would spin to 7,000 RPM. Top fuel engines were turning 8,000. This tank engine was a diesel locomotive trying to be a sprint car. Enter the lunatics who decided to try anyway. The most famous was TV Tommy Evo, already a legend in drag racing circles. But he wasn't the first. That honor goes to a largely forgotten racer named Ted Teixeira from California. In 1963, Teixeira acquired an AV-1790 from a Los Angeles surplus dealer. He spent 6 months figuring out how to mount it in a custom chassis that could handle the weight. The chassis had to be completely reimagined. Normal dragster frames used thin-wall chromoly tubing, maybe 1.5 inches in diameter, with 0.095-inch wall thickness. Teixeira's creation used 3-inch diameter steel tubing with quarter-inch walls. The frame alone weighed 800 pounds. The rear axle was from a truck. The transmission was a modified Allison unit from a tank. The whole car weighed forward 200 pounds. For reference, a competitive dragster of the era weighed 200 pounds. The first test runs were disasters. The engine made torque, endless, biblical torque. But it came on like a sledgehammer. There was no finesse. You'd stage the car, the light would turn green, you'd floor it, and one of 3 things would happen. 1, the tires would break loose and you'd smoke them all the way down the track. 2, the tires would hook and something in the drivetrain would explode. 3, the tires would hook, nothing would break, and the front end would come up so violently the car would nearly flip backward. Teixeira experimented with gear ratios. The tank transmission had 6 forward gears, but they were all wrong for drag racing. First gear was a 7.56.1 granny gear, designed to get 46 tons moving from a dead stop. Sixth was 0.71.1 overdrive for cruising at 30 miles per hour. Neither was useful for covering a quarter mile as fast as possible. He ended up locking out most gears and running third and fourth only, with a 2.89.1 rear axle ratio. The cooling system required complete re-engineering. In the M47 tank, 2 massive fans driven by hydraulic motors moved 14,000 cubic feet of air per minute through carefully designed ducts. Teixeira couldn't replicate that in a dragster. He tried electric fans. They melted. He tried belt-driven fans. They robbed too much power. He ended up with a hybrid system using alcohol injection directly into the cylinders for cooling, similar to what fighter planes used for emergency power. It worked, but barely. Here's the thing about the Continental AV-1790 that most people don't understand. It wasn't actually designed for maximum power. It was designed for maximum reliability at moderate power. The compression ratio was only 6.7.1. Compare that to a racing engine at 12.1 or higher. The valve timing was conservative. The fuel system was primitive by racing standards. In tank configuration, it used a Marvel Hibler carburetor designed in the 1940s. It ran on 80-octane gasoline. Teixeira knew there was more power available. He raised the compression to 8.5.1 by milling the heads and installing pop-up pistons. He threw away the Marvel Hibler and installed 4 Weber 48mm carburetors. He reground the cam for more aggressive timing. He converted it to run on methanol. With these modifications, he was getting close to 1,000 horsepower. But power wasn't the only problem. The AV-1790 used a 24-volt electrical system. All automotive components were 12-volt. The starter motor alone drew 300 amps. Teixeira had to carry 2 truck batteries just to start the engine. The ignition system used a magneto the size of a coffee can. When it fired, it would interfere with timing equipment at the track. The first public runs were at Lyons Drag Strip in Long Beach, California, in October 1963. The crowd didn't know what to make of it. This thing didn't sound like a drag car. The exhaust note was a deep, thunderous bellow that you felt in your chest. At idle, it sounded like distant artillery. At full throttle, it was like standing next to a B-17 bomber on takeoff. Teixeira staged the car. The Christmas tree dropped. He launched. The front wheels came up 3 feet. The car lurched forward like a drunk rhinoceros. The tires hazed the entire length of the track. The time slip read 13.74 seconds at 98 miles per hour. For reference, a stock 1963 Corvette would run 14.5 at 99.9 in lap. This 4,200-pound monster with 1,000 horsepower was barely faster than a production sports car. The problem was traction. All that torque was useless if you couldn't put it to the ground. Tire technology in 1963 couldn't handle it. The best slicks available were M&H Racemaster 11 Poru 16s. They were designed for cars making 400 horsepower, not 1,000. Teixeira tried everything. He moved weight around, he softened the suspension, he tried different tire pressures. Nothing worked consistently. Other racers took notice. If Teixeira could make it work, maybe they could too. By 1964, 3 more tank-engine dragsters appeared. Wild Bill Alexander in Texas built one using an AV-1790 from an M46 tank. The Ram Chargers team from Chrysler experimented with one in Detroit. Even Don Garlitz reportedly looked at the idea, though he never built one. The most successful was built by Jim Lidle, who took a different approach. Instead of trying to make the tank engine work in a conventional dragster chassis, he built the chassis around the engine's characteristics. His car was even heavier, 4,800 pounds, but it was perfectly balanced. He used a 2-speed Powerglide transmission from a Chevrolet, modified with heavy-duty internals. He kept the engine mostly stock, focusing on reliability over power. Lidle's approach worked better. His car ran consistent 12.8s at 108 mep. Not earth-shattering, but reliable. He could make run after run without braking. At match races, while other cars were in the pits fixing broken parts, Lidle's tank-powered monster would make exhibition runs all day long. The crowd loved it. But the real breakthrough came from an unexpected source. The U.S. Army's Aberdeen Proving Ground in Maryland had been experimenting with high-performance versions of the AV-1790 for experimental tanks. They had developed a fuel-injected turbocharged variant that made 1,200 horsepower. When word got out, drag racers went crazy trying to acquire one. Only one racer succeeded. Harry Hibler from Ohio somehow acquired a prototype engine through channels that remain unclear to this day. Some say he had connections at Aberdeen. Others claim he bought it from a scrap dealer who didn't know what he had. Regardless, Hibler had the Holy Grail, a tank engine that could actually compete. Hibler's build was different from the others. He understood that weight was the enemy. He built an aluminum chassis using aircraft construction techniques. He eliminated the tank transmission entirely, using a direct drive with a centrifugal clutch from an industrial application. He stripped every unnecessary component from the engine. His complete car weighed 3,400 pounds, 800 pounds lighter than Teixeira's. The turbocharged engine changed everything. Turbocharging was almost unknown in drag racing in 1964. The technology existed, but nobody had successfully applied it to a competition car. The tank engine's turbo was massive, a Schwitzer 4LE designed for diesel locomotives. At full boost, it pushed 28 psi. The intake air temperature would exceed 400 degrees Fahrenheit. Hibler had to solve problems nobody had encountered before. The turbo lag was measured in full seconds. The car would launch softly, then the boost would hit like a hammer blow halfway down the track. The acceleration curve was completely backward from a normal drag car. Instead of accelerating hard early and tapering off, it would accelerate harder the faster it went. The first runs at National Trail Raceway near Columbus were promising. Hibler ran 11.92 at 118 mph. That was competitive with mid-level dragsters of the era, but the real shock came when he opened it up at a match race in Indianapolis. With a good launch and the turbo spooled properly, he ran 11.23 at 126 mph. The drag racing world was stunned. i.e., tank engine had just run faster than many purpose-built race engines. But success was short-lived. On his next run, disaster struck. The turbocharger, spinning at 90,000 RPM, exploded. The turbine wheel, made of Inconel superalloy and spinning with the energy of a small bomb, exited through the hood. Shrapnel destroyed the intake manifold, 3 cylinders, and most of the car's front bodywork. Hibler was unhurt, but the engine was destroyed, and it was irreplaceable. The explosion highlighted the fundamental problem with tank engines in drag racing. They were never designed for this. Every component was operating beyond its design parameters. The AV-1790 was engineered to produce 810 horsepower at sea level, 600 horsepower at 10,000 feet altitude, in temperatures from 50 to 120 Fahrenheit, while being maintained by 19-year-old soldiers with basic tools. It was not designed to be pushed to 1,200 horsepower and subjected to violent acceleration cycles. The connecting rods were the weak point. They were massive forgings designed for steady-state operation. Under drag racing's violent loading and unloading, they would stretch and eventually fail. The crankshaft, a 200-pound forging that looked indestructible, would develop stress cracks after just a few runs. The cylinder heads, designed for air cooling, would develop hot spots when converted to liquid cooling. By 1965, the experiment was largely over. Conventional drag racing engines had evolved rapidly. The new 426 Hemi, with a supercharger, was making 2,000 horsepower. Keith Black was developing aluminum engines specifically for drag racing. Tire technology had improved dramatically. The tank engine's advantages, reliability and cheap horsepower, no longer mattered. But the story doesn't end there. The lessons learned from these tank engine experiments influenced drag racing in unexpected ways. The turbocharging experiments led directly to the turbocharged funny cars of the 1970s. The chassis engineering required to handle 3,000 pounds of engine taught builders about weight distribution and balance. The cooling system innovations found their way into other applications. Some of these cars survived. Teixeira's original is in a private collection in California. It still runs, though the owner rarely starts it. The fuel system requires 2 hours of preparation. The starting procedure involves 27 separate steps. When it does run, it still draws crowds. The sound is unlike anything else in motorsports. Lidle's car was discovered in a barn in Ohio in 2018. It had been sitting for 40 years. The new owner spent 2 years restoring it. At the 20-20 Hot Rod Reunion in Bowling Green, Kentucky, it made exhibition passes. It ran 12.95 at 106 mph, almost exactly what it ran in 1964. The crowd went wild. The technical legacy is significant. These experiments proved that unconventional power sources could work in drag racing. They showed that torque without traction is useless. They demonstrated that weight distribution matters more than absolute weight. They pioneered turbocharging in a motorsport application. They pushed the boundaries of what was possible, even if what was possible wasn't particularly practical. There's a philosophical element here, too. These tank engine dragsters represent a uniquely American approach to problem solving. Take something designed for one purpose, completely reimagine it for another purpose, and see what happens. It's the same spirit that put a Rolls-Royce Merlin engine in a P-51 Mustang or a Porsche engine in a Volkswagen bus. It's engineering without boundaries, constrained only by physics and imagination. The tank engine dragsters also represent a time when drag racing was more experimental. Today's NHRA Top Fuel is a spec series in all but name. Everyone runs the same basic engine design, the same chassis configuration, the same tire size. Innovation happens in tiny increments. In 1964, you could show up with a tank engine, and as long as it passed basic safety inspection, you could run. Would it work today? With modern technology, absolutely. Modern traction control, better tires, stronger materials, and computer modeling could solve every problem those pioneers faced. You could build a 2,000 horsepower turbocharged tank engine that would hook and run 8s in the quarter mile. But why would you? Modern racing engines are lighter, more powerful, and more reliable. That's not the point. The point is that someone tried. Multiple someones. They took an engine designed to power the ultimate expression of mechanized warfare and turned it into a drag racing engine. They failed more than they succeeded, but in failing, they learned. They pushed boundaries. They entertained crowds. They became part of drag racing folklore. The Continental AV-1790 was a masterpiece of military engineering. It powered M46, M47, M48, and M103 tanks through Korea and the Cold War. Over 12,000 were built. They served in 21 countries. In military service, they were legendary for their reliability and durability. Tanks with these engines are still running today, 70 years after manufacture, but for one brief, insane moment in the mid-1960s, they were also drag racing engines. They proved that with enough determination, you could make anything work. Sort of. They proved that bigger isn't always better, but it's always more interesting. They proved that American hot rodders will try absolutely anything in the pursuit of speed. The next time you see a modern top-fuel dragster with its 11,000 horsepower engine the size of a refrigerator, remember the tank engine pioneers. They walked so others could run. They showed that there are no bad ideas in racing, only learning experiences. Some of those experiences involve 3,000-pound engines that barely work. But that's what makes it beautiful. The tank engine dragsters remind us that engineering isn't just about optimal solutions. Sometimes it's about seeing how far you can push an idea before it breaks. Sometimes it's about taking the most inappropriate tool for the job and making it work anyway. Sometimes it's about the journey, not the destination. Even if that journey is a 13-second quarter mile in a 4,200-pound monstrosity that sounds like the end of the world. What's the craziest engine swap you've ever seen? Let me know in the comments below. And if you enjoyed this deep dive into one of drag racing's weirdest chapters, hit that subscribe button for more stories of engineering madness. Until next time, keep those engines running, even if they're tank engines.